All right, so nice to see such a big crowd. My name is Martijn Tideman. I'm the product director within TAS, which means I'm overall responsible for all the product development. It's a pretty nice job. So today I want to introduce you to our vision on how to develop and validate automated vehicles. I'd like to start with a short video. Went kind of viral on the internet a couple of weeks ago, so maybe you've seen it. It's still nice to watch it again. So luckily, this automatic emergency braking system on the Volvo truck functioned well, and there was no accident. Not everybody's so lucky. So if you look at the accident statistics, you know, there's very steep targets in the US, Europe, Asia to bring it down to zero. And the last couple of years, we're not following that trend anymore. So apparently, the current safety measures have reached their limits. In order to really reduce more, we need to do two things. First of all, to eliminate the driver. Why? Because drivers, humans, are responsible for approximately 90% of all the accidents. Secondly, we'll need to, improve occupant safety. So even automated cars, they will still end up in accidents every now and then it's, a matter of protecting the occupant as good as possible. Well, this is exactly in line with the two business lines of TAS, so smart automated driving and safe occupant safety. Are we developing those systems by ourselves and supplying them to the automotive market? No, we're not doing that. We are helping our customers, the international automotive industry, to develop those systems across the V cycle. So all the way from research via engineering and testing to the final validation and certification. So in other words, we're connecting simulation and testing. Our customers, the worldwide automotive industry, we have basically every OEM and tier as our customer. And it became even better a couple of months ago when Siemens acquired us. So Siemens is a strong company, have many simulation solutions and test facilities in-house. So together with Siemens, we're now offering a complete development chain for mechanics, electronics, for the verification and validation of automated driving systems. So back to the headline, connecting simulation and testing. So why do we need to test? By the way, these are some pictures of the TAS International Test Facilities in the Netherlands. You need to test because in the end, you need to verify and demonstrate that the physical product complies to the specific requirements and also the quality standards that the OEM has set and that the regulator has set. However, there's also some problems with testing. You can only handle so many real-life use cases, so either 10 or 100 or 1,000 or perhaps even 1 million, but certainly not 1 billion or 10 billion or 100 billion. Secondly, quite often it's done in an emulated environment, so it's real, it's physical. However, it's controlled. It's not real humans, it's dummy models, for example. So simulation very nicely complements this. So simulation, of course, you can theoretically do all real-life use cases. So indeed, the 10 billion or 100 billion, it's quick, it's cost-effective, it's safe, and it's perfectly reproducible. So that's why we at TAS strongly believe in the combination of simulation on the one hand and testing on the other hand. Let me dig a little bit deeper on the simulation solutions that we offer. So with Siemens now, we can cover the complete vehicle. Traditionally, within TAS, we only focused on the most important interfaces between a vehicle and the surroundings. So being the sensors, line of sight sensors, camera, LiDAR, radar, but also the radio, communication, V2X, DSRC, covered by our flagship product, PreScan. Then the one and only physical interface between the vehicle and the road, the tires. So a couple of square inches of rubber, but very important. Tire behavior determines like 30 to 40% of the complete behavior of a car. Especially if you think about automated vehicles, they need to brake and steer. The only way they can transfer these forces to the road are via the tires. Last but not least, the only part of the world that's not outside the vehicle but inside the vehicle, the humans. So we supply Marimo Active Human. And here's some, typical use cases of PreScan. So you see an adaptive cruise control in the top left corner based on the radar and the stochastic sensor models. You see a lane keeping assistance based on monocamera in a scenario where there's some weird things going on with the lane markers because of the roadworks. You see a parking assistance based on ultrasonic, and on the top right corner, you see something very nice, which is the combination of pre-scan for the world and sensor modeling and Marimo Active Human for the human modeling. And if you look carefully, you see that the Marimo Active Human simulation already starts 2 seconds before the impact. This is very necessary because due to the braking and the steering actions of the car, the human occupant gets already a little bit out of position, which in turn has an influence on how he or she is positioned at the moment the crash happens, which in turn has an influence on how to optimally activate your restraint systems, your seat belts and your airbags. Now, in this example, the human is positioned correctly, in the default position. But imagine automated vehicles. Humans are perhaps turned 90 degrees. They're perhaps asleep, laying down. They're doing whatever in the car. So part of the 1 billion scenarios is not only scenarios outside the car in the world, it's also scenarios inside the car. And we at TAS strongly believe you need to test these as well, because in the end, it's not only about fender benders, it's also really about the safety of the people inside. Let me dig a little bit deeper on the physics-based sensor models that are present in pre-scan. So here's an example of our camera model. It features lenses, color filter arrays, image sensors, etc. But that's not everything. You also need to work on the world, because if your sensor is susceptible to infrared light, if your world simulation is only RGB, red, green, and blue, that's not sufficient. So our world model, for example, is full spectrum. Same for the radar simulation. This is our newest radar model based on ray tracing. So you can study multipath effects and MIMO and interference even between radar sets. I'm not a radar expert myself, but whenever I show this to radar experts, they fall off their chair. They're like, this must be real data. No, it's not. This is simulated, and it comes from pre-scan. In addition to the physics-based sensors, we have some ground truth sensors, or segmentation sensors, or annotation sensors, if you will, and they're typically used to, as an objective benchmark to, get the performance of the system right, as well as to supply input to neural networks. So if you want to train neural networks, you have these annotated images that you need to feed. So with pre-scan, you can generate these very easily, and these are just some snapshots from recent projects we did with DFKI, Artificial Intelligence Research Institute in Germany, as well as Siemens before the acquisition, actually. And you see how real-world images are replicated into pre-scan, and then from pre-scan, you can automatically generate these annotated images. Okay, so far I've shown you a couple of, let's say, ingredients with respect to tooling. So I'd like to finish my presentation with demonstrating how we think you should use these tools in conjunction with each other. So in the end, you need to develop a vehicle that needs to function well in the real world, right? And you as an OEM or the regulator needs to have confidence that this goes well. So what we say you need to model the vehicle. You have to make a digital twin of the vehicle. So typically consisting of the vehicle dynamics, the engine, but also the sensors, the algorithms, perhaps the backend or the cloud if it's an automated or a connected vehicle. But that's not enough. You need to make a digital twin of the world as well, typically consisting of the static world models, the streets and the houses and the buildings, the dynamic world models, typically the events, the traffic, but also the occupant models. Remember, the part of the world that's inside the car. There's many variations there. Then you have a body of requirements, external requirements put on to you by the regulator or by consumer testing organizations, but also the internal requirements that you as an OEM have for your own product to sign it off. And usually the external requirements are a subset of the internal requirements. So basically with these three databases, you enter the V&V environments. So that's our term for verification and validation environments or execution environments. You have completely virtual environments like software in the loop running on big clusters. You have completely physical environments, test tracks, laboratories, field tests. And you have a couple of things in between. mixed environments, typically hardware in the loop, driver in the loop, and a vehicle in the loop. And as you can see with the arrows, you have many variations in the scenarios, for example, 1 million or 10 million. You also have variations in the vehicles, because a vehicle has different engines, different suspension settings for different countries, different gearboxes, different bodies, right? So that's easily another 1,000 or 10,000 variations, and you have to throw these in the mix, right? And you have to test this against the requirements. Okay, once you're done with the virtual stuff, we think you should reduce the amount of scenarios a little bit, because you only want to focus on the most difficult things. Plus, the lower you get in this box, the more time-consuming and expensive it becomes. So just to give you a quick example of how such a thing would look in each box. So you start with full virtual simulations, typically run on clusters. So this is a scenario, run over and over again with different parameters. Typically the weather here and the light circumstances. So it's sunny weather, now it's dark. Next scenario, it will be raining, and you see it has an influence on how the vehicle performs. This is a hardware in loop example where we inject our physics-based sensor data, camera, radar, LiDAR, into central automated driving processing units, typically the Drive PX from Nvidia or the DRS360 from Mentor. Mentor, by the way, is also a Siemens business acquired recently. And I have a couple of movies about that, how that would look. So run that. So this is injecting pre-scan camera images into the Drive PX, and then running the free space detection algorithm that's supplied as part of the DriveWorks. That functions pretty good. Another example is here, the Mentor DRS, where we not only supply the camera images, but also the the LiDAR data, and the Mentor algorithms, they detect the pedestrians and the vehicles, etc. Okay, last but not least, we have test tracks in the Netherlands, but we're also partnering with test tracks around the world. For example, the American Center for Mobility in Ypsilanti, Michigan, also known as the Willow Run facility. It's a huge facility, I think 1 by 1 mile or 2 by 2 miles. And we have played a role in the design phase and also now in the operation. It's been constructed during the last couple of months, and it's open now. Okay, let me get back to my introduction. You saw this movie, The Almost Accident. And if you look carefully at the brand of the truck that's braking, it's a Volvo. 3 years earlier, we shot this movie at Volvo Trucks in Sweden. Actually, we didn't shoot it ourselves, but it was a documentary on television, like BBC or Discovery, I can't really remember. And the Volvo team explained how they're developing the automated systems on board of the Volvo trucks. So, of course, they here crowd around the pre-scan simulations that they have used to develop the radar and camera sensors and algorithms, and then they go to the test track. And what's funny is that on the test track, they're not only testing, in this case, the second truck, which has been developed using pre-scan, but the first truck that has to make a controlled lane change is also operated by pre-scan. So pre-scan functions as a preprocessor for the test tracks as well. That was my presentation. So thank you for your attention.